Lecture 2 of Let's Make a Diels-Alder. Now it's going to start getting a little hairier because, of course, we're going to talk about stereochemistry. We'll save regiochemistry and synthesis for the next mini lecture. Alright, quick recap. We know that the Diels-Alder is characterized by the fact that there's no strong nucleophile, no strong electrophile. We've just got a bunch of pi electrons. Dieneophile, heat it up, and you get a cyclohexene as part of your product skeleton. There we go. There's the Diels-Alder. What should be evident from reading the textbook is that the diene should be electron rich and the dieneophile should be electron poor. So it's not like we have a strong nucleophile, a strong electrophile, but the Diels-Alder works best if the diene is electron rich and the dieneophile is electron poor. So for example, when we look at this pair of reagents for the Diels-Alder, root, we have an electron withdrawing nitrile on the dieneophile, making it electron poor, and we have nitrogens pumping electron density into the diene by resonance, of course. I can't even possibly draw these because my arrows are going to be too big. But basically, we've got electron density pumping into the diene from the nitrogens, and that should give us a very facile Diels-Alder product. So we've got this guy, and our cyclohexene right here with our nitrile right there. So Diels-Alder product number 1. On our bottom example, that is not our diene because it's not conjugated. Alright, so that's got to be our dieneophile, and you can see that it's electron poor because I have an electron withdrawing carbonyl. So this is my dieneophile, and oh, that's not my dieneophile, it's my target. I should have figured that out. That's my target molecule. And why should I figure that out? Because I got a cyclohexene there. So what this is illustrating, I mean, it could be a dieneophile as well, and we could just keep going this direction, but that's not what I'm trying to tell you here. What I'm trying to tell you here is that when I look at this as a target molecule from a Diels-Alder, I could break it down one of two ways. I could break it down by considering those retrosynthetic electron movement arrows, and that gives me this diene and dieneophile. Alternatively, I could go ahead and look at the other possible retrosynthesis as indicated by these electron movement arrows. So boom, 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 and that gives me this diene and dieneophile. Well, which one's better? Well, the one that has the electron poor dieneophile is better, and the one that has the electron poor dieneophile is that guy, because again, this is an electron withdrawing substituent. I could show this resonance contributor that pulls electron density out of my diene. In this case, my dieneophile, in this case it's an alkyne. Since that pi electron density is being pulled out of the alkyne, that makes it electron poor, and therefore a better match for this diene. So we'll talk more about synthesis in the next mini lecture, but as you can see from just this example alone, there's always two ways to break down a cyclohexadiene like this. All right, moving on. Let's get to stereochemistry and regiochemistry. When I have this diene and dieneophile, remember at the end of the last mini lecture we said, well, I could put the dieneophile so the carbonyl is pointing up or pointing down, and that leads to two regioisomers. That's regiochemistry. And when I have this diene and that dieneophile, ooh, all of a sudden, stereochemistry-wise, it's just starting to get pretty ugly. Here I've got just a few of the many possibilities. Both methyls up, both methyls down, up, down, down, up. Oof. Oh, stereochemistry rears its ugly head yet again. So let's look at that in some gory detail. It's all about orbital overlap. Okay, so the Diels-Alder forms from a concerted reaction as the orbitals on the LUMO match with the orbitals on the HOMO, have a 6 pi electron reorganization of the pi system. Now, as with all alkene reactions, my reagents can approach from the top side or from the bottom side. And that's what allows us to figure out the stereochemistry. So example number 1. What happens when it's the dieneophile that has stereochemistry? And of course, the diene and the dieneophile are achiral. So that means we must end up with a racemic mixture. And why are they achiral? Because there's no stereocenters and because they're planar. They both have a plane of symmetry, that being the plane of the screen. So here we go. We're going to heat those up and get a Diels-Alder to take place. And there is our Diels-Alder product. Just draw your electron movement arrows and you get your cyclohexene. Now note, the carbonyls, the dialdehyde here, the carbonyls are on opposite sides of the double bond, and so they must end up on opposite sides of the cyclohexene ring. In other words, the stereochemistry is retained. You can see that a lot more clearly if you look at the transition state through which the reaction takes place. So it is invariably a boat transition state when the Diels-Alder takes place. And why would that be? Well, that would be because, of course, we need to have these orbitals overlapping. So, as my diene and dieneophile overlap, they form our new bond. Here's our cyclohexene. It's in the boat configuration. And if I just rotate that boat, all I'm doing here is just redrawing this, kind of twisting this up that direction, you can see how those two are a match. So I've got trans in the dieneophile, I've got trans in the product. If I start out with a cis dieneophile, I'm going to end up with a cis product. Now note, this is going to be racemic, and this is going to be not racemic. I'll let you think about why that is not racemic, and get back to me on that if you have a question. All right, what happens when it's the diene that has stereochemistry? So here is an example of a diene that has stereochemistry. We have the E alkene geometry in this diene. What you want to do in this case is take yourself a little lasso and lasso those two hydrogens together. Okay, so those guys are going to stay constantly tied together as the Diels-Alder takes place. So here I am, I'm going to do my Diels-Alder, show my electron movement arrows, and get my cyclohexene. What I'm not showing here is the stereochemistry. This is the same example that we were, well, close to the same example we were looking at earlier. All right, so we've got to think about all four of those stereocenters. Ye gads, that means there's 16 possible stereoisomers. Well, earlier we showed that these were some of the possibilities. That's only four. I can tell you that the two on the right aren't formed. What's up with that? Well, if you look at the two on the right, and it's that playing with your mind's eye, stereochemistry is so hard, but basically you need to flip this guy upside down and you'll see that these two are a match. And if you compare these two carefully, you'll see that those two are a match. So we don't need to draw those two. They've already been drawn. Oh, how about this one? Let's look at this special example of stereochemistry. It actually will inform our previous example. So this is basically an example of a bicyclic molecule. It's kind of hard to draw this, but basically, if I show my electron movement arrows for my Diels-Alder, what's happening here is I'm tipping this bridgehead, as we call it, up in the air. So here is my cyclopentadiene. Oof, that's kind of hard to see. And here, obviously, is my cyclohexene ring. So I've got two stereocenters here that I'm paying particular attention to, the ones with the orange dots. How do we determine how this molecule is going to be formed? Well, the two planar pieces, the diene and the dieneophile, could overlap in such a way that the pointy part of the cyclopentadiene is really, pointing towards the other part, and that's called exo. Or we could put those two together so that they're actually kind of overlapping with one another. So we've got exo or endo. Now, those are kind of hard to remember. Here's the way Nancy likes to try to remember them. So if you think of this part of the molecule, is kind of looking like the roof of a house, see? Right? So here are the walls of the house, and maybe here is the door of the house and the window, and you can even imagine maybe this is a chimney with smoke coming out of it. So that's a house, maybe. If you think of it that way, then what you can see is this bit is inside the house. See how it's inside the house? Endo inside. And this one, exo, it's all sitting outside on the outside. It's kind of like a sunroof off to the side of the house, maybe. Maybe? Maybe? So that's how you can keep exo and endo straight, right? Maybe. Oh, sigh. Well, the bottom line is, in this particular case, in these kinds of cases, endo is favored, all right, and exo is disfavored. We hand wave our way through this by saying that there's some kind of funky overlap between these two pi systems that stabilizes the transition state. So the bottom line is endo is what's favored, exo is disfavored, and what you get then is a racemic mixture of the two endo products. So when it gets right down to it, so these two actually are representations of the exact same thing. These two are a perfect match. If you really want to understand it, you should make a model, and I will remember to bring a model, some models of these to class to hand around. Now this whole exo-endo thing can actually be used to explain in much more gory detail this example, not this example, this example. So if you want to really learn it, go ahead and re-examine that example just for fun. Alright, so that's it for stereochemistry. That should probably have given you a pretty good headache, and we will do many more examples in class.